We just saw how the source filter model is used to model voice and produce voice sounds. Now we're going to talk about a technique that's used especially to construct the filter part of the source filter model, and this technique is called LPC. LPC stands for linear prediction coding, and the basic model is very simple. It's shown here as this summation sign. What this means is that we are attempting to predict each sample, S sub n, as a weighted sum of the previous samples where the weights are A sub I, they're arbitrary, and the previous samples are S sub n minus I, and we use P is the number of weights that and the number of previous samples that we look at. This formulation gives rise to an all-pole filter. So in other words, a weighted sum of samples is a filter, and the response of this filter consists of resonant peaks. So where have we seen resonances before? Well, remember vocal formants and that graph that I showed of two formants determining what vowel sound we're hearing? Well, that's what we're doing. We're analyzing the signal to determine what those formants are. So LPC analysis finds a filter characterized by these coefficients A sub I, the filter that best approximates the signal spectrum. Just a little more detail, we typically choose P rather carefully or deliberately to be a somewhat small value, I think normally less than 20, so that the approximation, the signal approximation is not extremely good, it's kind of rough, and so there's enough detail in the filter approximation to represent the main formants, but not enough detail to give us the exact wave shape or other details of the spectrum. And that's what we're trying to do. We're trying to pull out these formant frequencies and width and height and so on. There's a physical analogy to what LPC does, and that is a tube, physical tube with a varying cross-section. Why is that important? Well, if you think about the vocal tract, here are vocal folds injecting pulses into a tube, which is your throat and your mouth and all the way to your mouth opening. It's not actually a simple tube, because sound comes through your nasal passages and your nose as well. And if you don't think that's important, we'll hold your nose and you'll sound like this. So there's obviously importance in the nasal cavities in terms of changing the sound of your voice. But anyway, this is a simple model. We're putting sound through a tube and varying the cross-section of the tube in the same way that your tongue and your mouth are varying the cross-section of your vocal tract. Now, the second point I want to make is that we're not talking about a fixed shape. We're talking about a shape that's rapidly changing. So that's how speech is possible. We're making this sequence of vowel sounds and consonants by rapidly moving our tongue and our mouth and all these things that change geometry. And so that's why we really need LPC or something like it to frame by frame reanalyze the signal and re-estimate the geometry of this tube, or re-estimate the actual coefficient values that determine this filter, because the filter changes over time, and that's partly what makes it sound like speech. Here's a great example of this tube. This comes from the Exploratorium, but I've seen these in other museums. Maybe you've come across this thing. It's a wonderful example. What's happening here is we start with the vocal tract, which is a tube of varying diameter, and we sort of straighten that out and construct a plastic tube with the similar geometry, and then we put a source up to this tube, and the sound I'm going to play for you is actually a duck call. just vibrating pulses into this tube, but the geometry of the tube is going to make the sound like an ah. Here we go.
Ah.
Let me play it one more time.
Ah.
And you can find more of these on the web. It's kind of strikingly and eerily human vowel sounding, and it's maybe even more striking if you can actually physically see the sound coming out of a maybe lucite block of plastic. LPC actually creates an inverse filter. It's not applying the vocal tract filter to the sound, but it's the inverse filter. So in a sense, it removes the resonances. And when you do that, what you get out is a residual. So the residual is either considered to be an estimate of the glottal pulses, the source. And if you get a sequence of pulses, you can then use those to do pitch analysis and estimate the pitch of the source. Or if you do not see a sequence of pulses, you can assume that the source was noise, and you can use noise as a model for the source. When we take all of that into account, we get an overall LPC analysis system that looks like this in the picture. Over here we have an input signal. We're doing the formant analysis, which is the estimation of those A sub I coefficients. We apply the resulting filter to the input signal, and we get a residual. Then we can do pitch detection on the residual. The formant analysis, these A sub I itself, comes out with all-pole filter coefficients that we can use to construct the filter part of the source filter model. And then we can do an analysis to see if the input is periodic or not. So that gives us the decision of whether this is a voiced or unvoiced source. And we can also do amplitude detection to get the RMS, the amplitude, on a frame-by-frame basis. So for each frame of LPC analysis, we get not only the filter part of the source filter model, but looking at the source, we get an estimate of pitch and amplitude, and whether or not the source actually has a pitch, or maybe it's just a noise source. There are many musical applications of voice sounds and source filter models. One thing that's very common and has been pursued by many composers, and a very interesting thing to do, is replace the source with some other sound. So for example, rather than having a pitched source or a noise source that might simulate a real human voice, you can put in a recording of an orchestra and apply human sounding formants to the orchestra so that the orchestra sounds sort of like speech. Or you can put in very synthetic sorts of pitched source sounds, and the list goes on and on. You can also warp the filter frequencies to get sort of human-like but not really human filters. You can modify the source and the LPC coefficients to perform time stretching, so slowing the speech down or speeding it up. And there are some demos of doing LPC analysis and synthesis in the Nyquist distribution under the demos folder, and look at lpcdemo.lisp.